What's going on, you physics nerds? This is a quick video to go over what we are studying right now, which is projectile motion. Okay, so first things first, a projectile is an object that is moving under the influence of gravity only. So, for the purposes of this first part, I'm going to use this simulator. I'm going to turn off air resistance, and I'm going to leave the projectile at this angle, but I want you to notice something. So the first thing is, if I choose to show the overall, which is the total velocity vector with an initial speed or velocity of 18 meters per second, and I choose the acceleration vector, I want you to notice something about the projectile. I'm going to put it in slow motion and fire. Now, you notice how there is a arrow pointing downward. This is the acceleration due to gravity. That's what this vector is showing here. Okay, so this guy's not erasing properly, sorry. So if you notice, the projectile is constantly being acted on by gravity. Okay, so the whole time the projectile is moving, it's being acted upon by gravity only. Now, the next thing we want to pay attention to here is that the shape of the motion is a parabola. This is called a ballistic trajectory. So let me write down a couple of those things right now. So first thing is that a projectile is acted upon by gravity only. Look at my beautiful handwriting. The other thing is that the path is a parabola, also known as a ballistic trajectory. A trajectory is the course that something is on. Okay, so now for the next part, gravity is constantly acting on the object. Okay, so what we want to do now is look at the component velocity vectors. So let's fire it again. Now, if you notice, this horizontal, okay, x-axis component, that arrow remains constant. And you're going to notice that because of gravity, this vertical y-axis arrow or vector pointing upwards is going to constantly change. Okay, see how it's shrinking? Now, at the very peak, watch what happens. It disappears. And that's because even though the projectile is constantly moving to the side in the x direction, horizontally, at the peak, the projectile actually stops moving up or down. It actually comes to a total stop for a small fraction of a second, a millisecond or so, a few milliseconds. And then the projectile continues on. And now if you notice, that downward velocity vector is increasing because gravity is an acceleration, meaning it makes something change speed over time. In this case, gravity is accelerating the projectile downwards at negative 9.81 meters per second squared, which is from the acceleration due to gravity on the cover page of the reference table. And eventually, the cannonball hits the ground. Okay? So a few things here. So first, this motion, okay, where the cannonball, I don't know why it's not writing in a straight line. I give up. Anyway, if you notice halfway through the flight, okay, that's called the peak, and this is the maximum height. So this is the peak height right there, okay? And we have to write down a few notes here. So the velocity of the projectile goes to 0 at the peak. And the other thing is that the peak, as long as there's no air resistance, the amount of time it takes to get to the peak is half the total time it takes to hit the ground, which means that if you double that amount of time that it takes for the projectile to get to the peak, if you multiply that by 2, that's how long it takes for the projectile to hit the ground again. So let's write those down. So, a couple of things. What did we say? maximum height is the peak. At the peak, a few things. The velocity in the y-axis is 0 meters per second. The other thing is that the time to get to the peak is 1/2 of the total time it takes for the projectile to hit the ground. Okay? All right. If I can erase these things. This is super weird how it's acting like this. Oh well. I feel like doing this whole video over again. All right. So now we know that the projectile moves in an overall motion. Let's look at that again. But if we look at the component vectors, again, it's an up and down vertical motion in the y-axis and a left and right horizontal motion in the x-axis. And what we have to remember is that we have to use the trigonometric functions to separate the two. Okay? So to solve for the horizontal motion, which is the x-axis, we use cosine. Okay? So the equation ends up being the overall velocity cosine of whatever angle it's getting shot at with the capital Greek letter theta. And then the vertical motion in the y-axis, we must use sine. And the equation ends up being the overall velocity sine of the angle the projectile was launched at. Okay. All right, almost done. One last thing. What about the launch angles? So if everything else remains equal, watch this. So let's start with the large angle of 90 degrees, straight up. So if you notice, the cannonball goes straight up, takes a long time to hit the ground, 3.67 seconds. And the maximum height is 16.51 meters in this case. Okay, so a 90-degree launch angle causes the largest amount of time in the air before hitting the ground, the highest peak distance off the ground, which we call the height, but the projectile has no range. It didn't go anywhere. It landed where it started. Okay, now what if we choose an angle of 45 degrees, which is halfway between the ground and straight up? Okay, let's measure this. Now, obviously, you can see that the peak height is much lower than being launched straight up at 90 degrees. The time is the time to hit the ground is 2.59 seconds, which is a bit less than this. I guess I have to zoom back in. Am I being weird, program? Oh, well. Anyway, so we know that the projectile launched at 45 degrees takes less time to hit the ground, but if you look, the range is 33.03 meters as opposed to the 0 meters before. Now, what happens if we launch at an angle below 45 degrees? Okay, as you can see, the projectile barely made it off the ground, which means that it hit the ground much sooner, which means that its range, 25.3 meters, is less than 33 meters. What happens if I try a little bit higher than that, but lower than 45? Will it go as far? No. Okay, what if I try a launch angle that is greater than 45? Okay, the projectile goes further up, but it doesn't land as far away. What if I go even at a steeper angle? No. So in conclusion, we could see that if you want a projectile to go the greatest distance horizontally, you will use a 45-degree angle. Anything lower or greater than that, and you will have a lesser range. If you want a projectile to have the greatest peak height, you would launch it at 90 degrees. And there you go. And now one last thing. If we turn on air resistance and try that again, so here's a launch at 45 degrees with air blocking the projectile's path. That's called air resistance, like it's friction with the air. And let's launch without the air. All right, so we can clearly see that when there is air resistance, which is in real life, it greatly affects the distance and height that the projectile goes. So with air resistance, the projectile does not go as far or as high as without air resistance. Okay, so let's jot those down, and that's about it. So let's write down what we saw. So launch angles, 90 degrees, greatest height, largest time in the air, but the smallest range. "45-degree launch angle causes the greatest range, which is the largest distance in the x direction." Okay? And we also saw that anything that is at an angle of less than 45 degrees causes a lower range. Lower range, lower height, and less time in the air. It's called the time of flight. Okay? And lastly, we said that with air resistance, the range and height are reduced. Okay? So there we go. All right, quick summary. A projectile is acted upon only by gravity. The path it makes is a parabola. This is called a ballistic trajectory. The maximum height is known as the peak. At the peak, the up and down motion in the y-axis vertically is 0. The time it takes for a projectile to get to its peak, as long as there's no air in the way, is half the total time, which means the total time is just the time to peak times 2. The horizontal velocity is calculated using cosine. The vertical velocity is calculated using sine. A projectile launched at 90 degrees produces the greatest height, largest time in the air, but the projectile lands right where it started. 45 degrees will always produce the greatest range. Anything greater than 45 degrees, anything greater than or less than 45 degrees, really should put that, right? Anything greater than or less than 45 degrees will produce a lower range. If the angle is greater than 45, you'll have a greater height, but less range. If the angle is less than 45 degrees, you'll have lower range and lower height. Okay? But yeah, there you go. And with air resistance, the projectile gets blocked by the air because of friction, and the distance traveled and height are all reduced. Okay? If you need to copy any of that down, you can feel free to pause this at any point. And yeah, I'm a musician and a scientist. Clearly, my handwriting has nothing to do with either of those. All right. Later, your notes.